Unit 5, Thermochem, pages 48 to 53, Hess's Law. Principle of Hess' Law. Consider a series of steps where the height of one step is unknown. So here you have several steps, but you do happen to know the total height from beginning to end. Because height is a state function, the missing height can be found with this calculation. Question mark equals 30 minus 15 minus 5 equals 10. Hess's Law is based on the same idea as the steps. The value of delta H sublimation must be the same for both paths shown in these two equations, where path 1 is H2O as a solid, and then when it changes to a gas, we have the delta H of the sublimation. Or path 2, if you go from solid, then to liquid, then to gas, then the leap from here to the end is still the same, delta H of the sublimation. Both paths start with H2O solid and end with H2O gas. State functions like delta H only depend on the initial and the final state of the system. So the value of delta H sublimation could be determined along path 2 if you were to combine the heat of fusion to go from here to here and the heat of vaporization to go from here to here. Combined equals this total delta H of sublimation. So here, if we look at it in the stepladder graph, then we have the delta H of sublimation, where if you went straight from solid to gas, it would take this much heat. Or if you went from solid to liquid first, it would take this much, and then from liquid to gas, it would take this much. But if you combine these two, we still get the total overall amount of heat for the whole process. Instead of drawing pictures of reactions as series of steps, Hess's Law says that reactions can simply be added together to find the delta H of a total reaction for the combined reactions leading up to the total final reaction. So for example, the delta H of fusion going from solid to liquid can be combined with the delta H liquid to gas, which has a delta H of vaporization. And so when you combine these two, you might notice that because we have liquid on the right here, it's going to actually cancel with the liquid on the left here because they're on opposite sides. And what we're left with that's not been canceled is H2O solid yields H2O gas. And so when I combine this plus this, it's going to give me my total final delta H of this process here. So here's a Hess Law example. Here is the final equation that I'm shooting for. So, and then these are the intermediate reactions that I have to work with. My goal is to get these set up in such a way that when they cancel out, they end up leaving me with 2 carbons plus hydrogen gas yields C2H2 gas. So first, look at this equation. It's got C2H2 in common with C2H2 gas up here. But notice, this is a product while this is a reactant. And so what I want to do is reverse this reaction in order to get it to the product side. So I'm going to rewrite this equation in the reverse. And then reversing this equation means that I'm going to change the sign from negative to positive for this first delta H value here. And so here's the equation written in reverse, and now we know that this delta H is now positive instead of negative. Let's look at the second equation. Notice what it has in common with what I have above, the carbon solid. Notice that they are both on the left side of the equation, reactant side, so I do not have to reverse this one. However, because this has a coefficient of 2, I need this to also have a coefficient of 2. So what I'm going to do here is multiply this second equation to give all of my coefficients times 2, which is going to put a 2 here, a 2 here, a 2 here, and that means that my delta H value here is also going to be times 2. So I'm going to rewrite my new equation with the new coefficients down here. And finally, we'll look at equation 3, and it has in common with my equation above the hydrogen gas here. Notice that they are both on the reactant side, so I do not have to reverse the reaction. And notice that they both have the same coefficient, so I don't need to multiply this equation by anything. So now I'm going to recopy equation number 3 down below as well. So these 3 equations here should combine and give me this equation up here. So let's see if everything cancels properly. 2 CO2s on the left are going to cancel with these two CO2s on the right. And then my H2O liquid here on the left is going to cancel with this H2O liquid on the right. And finally, my oxygens, because these are both on the same side of the equation, they are going to combine or add together. And I need to go ahead and change this one to a fraction so they can add together. So really this is the same as 4 over 2. So 4 over 2 plus 1 over 2 is a combined total of 5 over 2 oxygen. And this 5 over 2 oxygen on the left side total is going to cancel with the 5 over 2 oxygen of the right side. So notice what I have not canceled out is these. So these have canceled because they combine to make this one. So I have left over 2 carbon solid plus hydrogen gas yields C2H2 gas. And you'll notice that this is identical to the equation up here, which it should be. So what that tells me now is in order to get the delta H for this reaction, I need to add together delta H1 plus delta H2 plus the delta H3 up above right here. And so when I combine these, it's going to be 1299.6 plus negative 393.5 times 2 plus negative 285.5, and that's going to give me a final answer of positive 226.8 kilojoules per mole. Remember that positive delta H's means that is an endothermic reaction. And so this final reaction right here is going to overall be endothermic. Example 5.17, we're going to calculate the delta H for this reaction right here using the heats of reactions given below. So first, I'll look at equation number 1, and I'm going to find what does it have in common with my equation, final equation up here. And notice we have H2O2 liquid as a common factor here. My problem is this H2O2 is on the reactant side, this one's on the product side, so we need to reverse reaction number 1, which means that this is going to change from being negative to a positive value. So I'm going to rewrite equation number 1 below. So here it is down here. We're also going to note one other issue. This has a coefficient of 2, this has a coefficient of 1. So I also need to multiply all the coefficients by 2. So that means that this delta H is going to also be times 2 when we use it in our calculations. So here we should have coefficients of 2 going all the way across the equation. Now let's look at equation number 2. And notice that it has N2H4 in common here. It has nitrogen in common here. And it has waters in common here. Now, I'm not going to actually change anything about my coefficients because this one and this one are what they should be. And even though this one is not, it doesn't mean that we're not going to have other waters later, such as in equation number 3. So I'm going to go ahead and leave this equation as is, and I'm going to rewrite it down here underneath equation number 1. Finally, I'll look at equation number 3, and notice that the only thing it has in common with my original equation is the 2 waters here. And so I'm going to just leave those on the right-hand side, and I'm not going to change the coefficient because I'm going to notice that these are going to end up combining with one another. So we're going to just leave all this as it is, and we'll rewrite equation number 3 down here. So just to make sure I've got everything aligned so that I end up getting this equation as my final, I'm going to just check to see that everything cancels properly. These 2 hydrogens cancel with these 2 hydrogens, reactant side versus product side. Notice that I have 2 oxygens as a product over here, and I have these 2 which combine together to form 2 O2s over here. So these 2 are going to cancel out with those 2. And then I'm going to, that's everything I need to cancel. So we have left over N2H4 liquid plus 2H2O2 liquid yields nitrogen gas plus, and then these 2 waters combine with these 2 waters because they're both on the product side to make 4 waters, which is identical to my equation up here, and so I had everything set up properly. That means now I can go ahead and calculate my delta H so my delta H of reaction is going to be equal to delta H of reaction 1 plus delta H of reaction 2 plus delta H of reaction 3, which is going to be 187.8 times 2 plus negative 622.4 plus negative 571.8. And that's going to give me an answer of negative 818.6 kilojoules per mole when I put that into my calculator. Here's your note card for this section. When you have the when you're trying to find the delta H of a reaction given multiple reactions, then the sum of each of the reaction delta H's should give you the delta H of the overall reaction. If you have to reverse an equation, then you're multiplying the delta H times -1, or you're changing the sign from positive to negative, or vice versa. If you multiply the entire equation by a new coefficient, this means multiply the delta H by that same value. And then finally, whenever you are trying to see if you have your overall reaction proper, anything that's on the opposite sides of the reaction are going to cancel with one another, but if it's on the same side, then they're going to combine with one another. And then everything that's not canceled should make up the desired reaction that you were going for.